Another subject from section 4, chapter 3. We're going to talk about the intermediate value theorem and the boundedness theorem. The intermediate value theorem says that if you plug in a number a into your function, so you're finding f of a, and you get a positive number, and then you plug in a different number b, and you get f of b is a negative number, or vice versa, that somewhere between a and b there exists some number, say c, such that f of c, the y value of c, would be 0. So somewhere between a and b there is an x-intercept, or there is a 0 or a root. So basically, if we kind of draw that out, we might have our graph like this. So here could be at a, here could be at b. So if we get some positive value for y on a, so maybe somewhere up here, and we get some positive value or negative value for b, somehow our graph has to, if it's continuous, all right, it's a polynomial, then somehow our graph is going to have to cross that x-axis here. It can cross down here and come back, maybe something like that. It could cross right there, maybe go straight through, but somehow it's going to cross in between a and b, and that's what the intermediate value theorem says. So that we can locate a 0 somewhere between a and b. Okay, so we want to use synthetic division, take this function and show that there's a real 0 between 2 and 3. Now, in order for there to be a real 0 between 2 and 3, that means that when I plug in synthetic division, my remainder for one of these has to be positive and one has to be negative. Right? So they can't both be positive. That doesn't show that there's a 0 there. There still might be, but that doesn't use the intermediate value theorem. So when you use synthetic division, list your coefficients, make sure everything's taken care of. We got 3, 2, 1, and 0. 0 on the second row there. We're going to add our first two rows together. So 1 plus 0 is 1, and then what goes in the box is 2 and 3. So we're going to do 2 first. 1 times 2 is 2, minus 2 plus 2 is 0. 2 times 0 is 0, minus 1, and we get negative 2 here, and 1 minus 2 is a negative 1, so that is a negative. Okay, so at positive 2, 1, 2, we're down at negative 1. Right, so 2, negative 1. Let's go ahead and plug in, do the same thing. 1, negative 2, negative 1, and 1. 0 in your second row. Going to add that first column together. 1 and 0 is 1. What goes in the box this time is 3. 3 times 1 is 3. Minus 2 plus 3 is 1. 1 times 3 is 3. Oops. Is 3. 2. 6, 7. So we get a positive 7. So you don't have to graph this, but I just showed that, hey, by the intermediate value theorem, IVT, there exists a real 0 between 2 and 3. Okay, because there's 2, negative 1, and then we got 3. 1, 2, 3, 4, 5, 6, 7, somewhere up here, right? 2, 7. So there exists somewhere our graph is going to cross through these two lines right here. So there exists some 0. It might be 2.5. It might be 2.1. It could be, infinitely many possibilities within there, but we know it does cross that line somewhere. And that's what all the intermediate value theorems suggest. So go ahead and do number 49 on page 331. or 330, 331. Number 49 goes along with this, and I'll do it at the end of this video. All right, the next theorem is the boundedness theorem. And basically what this, it kind of really helps once you find 1, 0 in your solution of any polynomial with degree 1 or more, then it helps you kind of eliminate your other possibilities. And I'll go ahead and type those out now, and then I'll discuss them. Okay, so here it is. So if C is a 0 of a polynomial, then you have two circumstances how the boundedness theorem can help. So if you found a 0, you can look at the bottom row of your synthetic division, and if they're all positive, okay, so if they're all positive, then you have no 0 greater than C. Okay, so what that means is if I'm doing synthetic division, okay, and my bottom row is a 1, 7, 3, 2, and 0, right? And I plugged in, say I plugged in 3. So 3 is greater than 0, right? And so then my bottom row is all positive. That means that there is no other 0 that's going to be greater than 3. And we kind of talked about this in class, right? I can't put in positives because I'm just going to get bigger and bigger and bigger and bigger and bigger as I put in bigger numbers other than 3. So all my other zeros must be smaller than 3. So that can eliminate all the rest of the positives for you that are bigger than 3. Now the second case is if C is smaller than 0. So if I plug in a number negative, say negative 3, and then my bottom row has to be alternating. Okay, so I could have 2, I could have negative 3, I could have 0, I could have negative 2, and then 0. Okay, so it's okay if 0 is in there. That's why it says as needed. But it alternates. So my bottom row alternates. I got 2, a positive, negative, and then 0. So negative can be positive here, and then negative 2, and then 0 again can be positive. So here it alternates, positive, negative, positive, negative, positive, negative. So since it alternates, that means there is no C less than 0. Okay, so all my zeros that exist, real number zeros, would have to be greater than negative 3. So that can eliminate some of your choices. So that kind of helps on figuring that out. Here, I'll give you an example. Okay, so here's our polynomial 2x to the 4th minus 5x cubed plus 3x plus 1. So we're going to find our possibilities. That is taking all the factors of our constant, which is just plus or minus 1, and dividing by every factor of the lead coefficient. So I got a plus or minus 1 divided by plus or minus 1, and then I got to take plus or minus 1 and divide by plus or minus 2. So my possibilities are 1, plus or minus 1, and plus or minus 1/2. So then we can go ahead and do synthetic division, list our coefficients, make sure nothing's missing. Here I have to the 4th, to the 3rd, I'm missing a to the 2nd, right? So I need to put a 0 in there, and then 3, and then 1, and then put a 0. So actually the nice thing about the boundedness theorem is that so I can take my possibilities and run it through and see what happens here and define my zeros. But what the boundedness theorem kind of does is, even if I put say 2 in here, even though I don't have that on my list, but if I put 2 in here and I come down, 2 plus 0 is 2, 2 times 2 is 4, 2 is not going to work, sorry. 3, if I put 3 will work. Because I want all positives, right? I want all positives down here, so if I put in 3, 2, 6, 1, 3, 3, 9, 12, 36, 37. So notice that all these numbers are all positive. So that means my answer, if I want a 0, that means that it's going to be smaller than 3. So this would help if you had a bigger list of possibilities, right? And you got all positive down here. That would eliminate some of them. So that kind of helps in a way. And then how about plugging in -1? So let's plug in -1. So 2, -5, 0, 3, 1, 0, we get 2. 2 times negative 1 is negative 2. So negative 7, that's positive 7, negative 7, negative 4, positive 4, and 1 4 is 5. So notice that these alternate. So these alternate, positive, negative, positive, negative, positive. So even though it didn't get us a 0 at the end, I can take this number and say, okay, well, it's negative, and I got alternating numbers. So what that means, it cannot be smaller than negative 1/2, right? So I can't do negative 2 or negative 3 or negative 4 and so on. So that eliminates all numbers that are smaller than negative 1/2. So that eliminates all those. So you know your list is somewhere between 3 and negative 1 for your zeros. So like I said, if we had a bigger kind of list of possibilities, this would definitely eliminate some of them, because I would only have my answers would be between 3 and negative 1. So that kind of helps you out there. Okay, so here's the last part of your homework from this section is page 331, number 49, 57, and 59. And then I'll go ahead and do them. Okay, so here's number 49. We got f of x equals 2x cubed minus 5x squared minus 5x plus 7. And we're going to use the intermediate value theorem to say that we have a 0 somewhere between 0 and 1. So how to prove that is we do synthetic division. Make sure they're all there. 3, 2, 1, 0. 0 in the second row. We're going to add those together, 2. And then we're going to place 0 in here and see if we get a positive or negative as our remainder. So that's, oh, why did I put, yeah, 0. Negative 5, that's 0. Negative 5, that's 0, and 7, so that's positive, right? So we get a positive there. And then we're going to do it again, but this time we're going to plug in 1. So this time we're going to plug in 1, start back out our coefficients, 2, negative 5, and 7. 0 in the second row, add those together, we get 2, 2, negative 3, negative 8, and negative 8, negative 1, so we get a negative. So somewhere, this kind of proves, this work, the work that you show here, proves because we have a positive, so f of 0 is positive, and f of 1 is negative. There has to exist, by the intermediate value theorem, there exists a point such that somewhere between 0 and 1 that it equals 0. So there must exist some point between 0 and 1 that gets a 0 as a y value. So that's number 49. It's just showing the work. So you can say by the intermediate value theorem there exists an x between 0 and between 1 that f of x, or maybe not use x, you could use a different letter, equals 0. So maybe like in the book they kind of do always like c. And remember, you can use any letter most of the time for anything. Just because they use a different letter, the letter just represents a number, right? So don't be caught up with the choices of letters that they choose. Okay, but we sometimes don't want to use the same letter in the same problem, because I don't want to use x because it already uses x in here. That's why I didn't want to put x in there. Okay, so there's number 49. Okay, so here's number 57, x to the fourth minus x cubed plus 3x squared minus 8x plus 8, and we want to see that there is no real 0 greater than 2. No real 0 greater than 2. Okay, so since that's positive, that means what we're trying to do is when we do synthetic division, this bottom row needs to be all positive numbers. And we just need to show that, right? So that we just do it. Put in 2 into the box, lead your coefficients, 1, negative 1, 3, negative 8, and 8. Make sure they're all taken care of, 4, 3, 2, 1, 0. And then we just run through it synthetic division, and my work here is my proof. So 2 times 1 is 2, 2 minus 1 is 1, 2 times 2 is 2, we get 5, we get 10, we get 2, we get 4, we get 12. So they're all positives, right? So there's my work. I'm not going to have, by the boundedness theorem, we are not going to have a real 0 greater than 2. Okay, so here's 59. We have our function f of x equals x to the 4th plus x cubed minus x squared plus 3. And we want to show that there is no real 0 less than negative 2. So negative 2 is negative, so that's what we want to show, that our bottom of our synthetic division is alternating negative, positive, negative, positive, negative, positive, or positive, negative. And zeros can be positive or can be negative. So we have our coefficients, which are 1, 1, negative 1, but I'm missing a linear term. I'm missing just a plain x, so I got to put 0 in there for that, and then 3 is my constant. 0 in the second row. Add these first two columns together. 1 plus 0 is 1. 1 times negative 2 is negative 2. Negative 2 plus 1 is negative 1. Negative 1 times negative 1, or sorry, negative 1 times negative 2 is a positive 2. 2 minus 1 is 1. Negative 2 times 1 is a negative 2, plus 0 is negative 2. Negative 2 times negative 2 is 4. 4 plus 3 is 7. So it alternates. So this number has to be negative, right? And then these have to alternate positive, negative, positive, negative, positive. So yes, we showed right here is our proof that we will have no real 0 less than negative 2.